So from a business implication standpoint, we can do a lot of different bivariate analyses, and the coefficient of determination indicates a lot in terms of the correlation between two variables. But for a specific example, we can perhaps look at someone who's trying to create a TV show and compare different eras of basketball, and they want to see how the three-point percentage influenced win percentage in this era in a few different years, and how the three-point percentage influenced win percentage in the previous era, and therefore they can have statistical evidence to back up their claims or to denounce their claims and so forth. And we can do that looking at the coefficient of determination for each of the different models that we present. So we will now talk about our next concept of control charts. And control charts are used to monitor processes over time, and their key attributes include variability and out-of-control points, which we'll talk about in a little bit. And it's worth mentioning DMAIC, which stands for Define, Measure, Analyze, Improve, and Control, because control charts are really a big part of the control step in this process. So when companies want to make sure their processes stay in control after implementing changes and improvements, control charts are often used. And this has a lot to do with Lean and Six Sigma, which we can relate to the business implications side of control charts. So at this time, we will go over to JUMP to look at an example of a control chart. So here we have our data set diameter, and we're going to go ahead and run the script for the control charts, but note that you can create your control chart yourself using Analyze, Quality, and Process, Control Chart Builder. But just for time's sake, we're going to go ahead and run the script. So when we run the script, we can see that we have an X bar in our chart of diameter, and for this specific example, we can see different diameters for different dates, and we can see the average, the UCL and LCL, and points beyond the UCL or below the LCL are considered out of control. And if our process is out of control, then we might need to make a few adjustments to make sure that our points are staying within the bounds of our UCL and LCL. And it's worth mentioning that we can see variability on these charts. And again, we use these charts a lot of times to make sure that our process is staying in control after we make improvements and changes to it. And these charts are an easy way to see, okay, do we have any points that are out of control? And if we do, then we'll need to go back in and make a few adjustments. And that has a lot to do with the business implications as well. But SAS Jump does a good job of allowing us to easily create control charts and then to view them and draw results from them. Our next concept is Pareto charts, and I actually like to refer to them as glorified histograms because they are basically histograms just with a few more details. So notice that each of the categories on the x-axis are put in order from largest to smallest. The cumulative percentage is also graphed on a secondary y-axis, and it can be useful in the business world when looking at different failure causes. And it's also worth mentioning the Pareto principle, which says that roughly 80% of the effects come from 20% of the causes. So I'm not going to spend a whole lot more time on this just for time's sake of the video, but we'll go ahead and look at one of these Pareto charts in JUMP. So here we have our failure data set, and we can simply see that we have failures and their counts. And we can go ahead and run the script. And notice how we have the failures on the x-axis from greatest to least, and we have the cumulative percentage as well. And we can see that the cumulative percentage for contamination and oxide defect is around 70%. So we can see that the majority of the failure comes from just two defects. So we can, for a business implication, we can really use Pareto plots to see different things such as failures, and we can see how much they're contributing to the total problem, And for example, we would definitely try to fix the contamination and oxide defect issue before we start looking at some of the smaller issues that aren't contributing as much to the overall problem. So the next concept that we have is reliability and survival. And survival analysis is a branch of statistics for analyzing the expected duration of the time until one or more events happen, such as death in biological organisms and failure in mechanical systems. So reliability and survival analysis is great for comparing things such as machines. You can look at which machine lasts longer between two or more, and are identical machines surviving the same amount of time. So we're going to go ahead and go over to JUMP and look at an example and see how reliability and survivability can be viewed in JUMP. So here we have a reliability and survivability data set, blenders. And if we go ahead and go to our survival script, we can see that we have a survival plot between automatic and manual blenders. And we're simply comparing the two and seeing, based on different time cycles, how long each of them survives. And we can analyze, again, two different things and compare the survivability of the two. So as we can see, manual blenders seem to not last as long as automatic blenders, and we can see that basically as time goes on, manual blenders seem to fail a lot sooner than the automatic ones. And again, for business implications, we can compare things such as cars and refrigerators, and we can compare within the same model or within different models and see how long they're lasting in comparison with one another. So our final concept is time series models, and simply put, time series models display variables and how they change with time. The x-axis is usually marked by time using units such as minutes or years, etc. And we can use a time series model to study trends in data and how variables change with time. And we can also use them to forecast into the future as well. So now let's move over to JUMP to look at a time series model example. So here we have our time series model example in JUMP, and it is GNP, or Gross National Product. And we can go ahead and go and analyze the Gross National Product as time increases. So we'll go ahead and go to Analyze, Fit Y by X. And again, as stated in the PowerPoint, our date will go on the x-axis, and our Gross National Product will be our y, or response. Go ahead and click OK. And this graph is not very hard to analyze. We can see that as time goes by, the Gross National Product steadily increases, and time series models are one of the most basic and most widely used models. So we have a lot of business implications that we can draw from them, and we can even look at things such as how many cars are selling as time goes by, and maybe we have a slump, and we can use that to predict a future slump and things such as that. Here are some extra references that I used in making this video, and I think SAS JUMP is a great tool for a lot of concepts and different models, and I've really enjoyed using it this semester, and I think it's a great tool for statistics, and I hope that you enjoyed watching this video. This is Engineering 305, Video Final Exam by William Herman. Thanks for listening.